So hello and welcome to Rational Expressions Lesson 4 for Shaughnessy's class. Standard disclaimer, please make sure you're attending class. That's where the full detailed lesson is. This is just designed to be a kind of quick summary. So we're talking rational expressions, which we talked about a few days ago, or in the last videos I guess, that these are polynomial fractions. We've also looked at some fraction operations and looked at some factoring. When we're reducing a rational expression, it's basically the same process, just there's factoring involved as well as the fraction operations. The steps, okay, when it comes to doing this. Steps, step 1, factor numerator. Step 2, factor denominator. Now, if it's already factored, then you don't need to do these, okay? But you have to factor them both, okay? And you factor them completely as much as you can. You look for common factor, so I'm going to put that in here behind. You look for GCF, okay? Greatest common factor, difference of squares, okay? That sort of thing. But you look for those, always look for greatest common factor first, because sometimes that's all there is. Once that's done, okay, cancel out the common factors in both the numerator and the denominator, okay? Okay, and then you just, if you've done it repeatedly, I mean, you may have to repeat, okay? I'm just going to write repeat if necessary. Okay. Okay, that's all is said and done. Okay. Now, that's all you have to do. Okay. The key thing is, in each case here, you must state the non-permissible values first. Okay, because the NPVs, even if they cancel out, we said that at the end of lesson 3, even if the NPVs cancel out, even if that part that does that cancels out, you end up with that non-permissible value. It's still part of the original expression. And so all this lesson is about, once you've got the basic steps, it's just about showing you various examples of what we mean by this. So you can start with some simple ones, i.e. example 24x over 3. Okay, this is an absolutely simple one. You go and start factoring this down, and so you can say that it's 3 times 8, there's your 24, and the x over 3. And you say, well, the 3's cancel, so this reduces to 8x. Okay. The other thing you need to look at, you always need to look at the non-permissible values and the non-permissible values from the original. So in this particular case, I'm just going to make sure this is focused. In this particular case, you look at this denominator here, and what it says is 3 cannot equal 0, which is good because 3 doesn't equal 0. So there's no NPVs, okay, because it didn't depend on x. So we're done. There's no non-permissible values. It's simplified to 8x. That's what it reduced to. Just like when you're reducing fractions, it's 8x over 1 if you need to do that. Okay, and you can just continue with various different examples going along here, looking at ones like this. X minus 9 over 3x minus 27. Okay, so you're going to factor the numerator. Well, the nice part is there's no common factor. That's not a difference of perfect squares. 9's a perfect square, but x isn't, so it's factored as much as I can. So that one's done. Down here I look for a common factor. There's a common factor of 3. I pull it out and I'm left with 1x minus 9. Now when I'm looking at this one, I say, well, wait, look at that. The x minus 9's are common, so I can cancel them out. Now the fraction is still there, so it's something over 3. You ask yourself, what is that missing imaginary something? It's not 0. There's always a 1. You could have said that it's 1 times x minus 9. There is always a hidden 1. So this particular one reduces to 1/3. It doesn't matter what x is. I mean, if you take this now, but this is what it's telling you. If you take this, make up an x. Ask your mother or father or brother, sister, grandma, grandpa, however it works out, ask them for a number between negative a billion and a billion. And whatever number they give you, if you plug it in and you do it correctly, you're always going to get 1/3. That's what this is telling you. It doesn't matter what x is, because it reduces, and x is irrelevant in that. The only other thing you need to do is you need to look for non-permissible values. Now, non-permissible values always come from the unsimplified form. So you have 3x minus 27 cannot equal 0. Okay? And so you move the 27 over. 3x cannot equal positive 27. Divide by 3, x cannot equal 9. This is your non-permissible value, 9. So when I talk about going and asking your relatives for a number between negative a billion and a billion, the only one that doesn't work is 9. If they say 9, the whole thing falls apart. But any other value, negative 82,264,308, if you use that and plug it in for x correctly, it will always equal 1/3. That's what you're getting here. Okay? Now there's all sorts of different examples that you can do, and essentially what happens is it just gets more and more complicated. If I look, I'm just going to do a few different examples. Okay, in class I do more. Okay? But if I did some examples here and I said example 2x squared minus 10x over 4x minus 20. And I say, okay, I've got to factor this down. Well, in the numerator, the first thing I see is a common factor of 2x. So I'm going to pull out the 2x, and that's going to leave me with 2 divided by 2 is 1. There was an x, or where's 2x's, sorry, I pulled one out, so there's 1 left. Then the minus 10 divided by 2 is 5. Okay, there was one x, I pulled it out, so it's out, so I've got that. And putting in the bottom here, now I'm looking at the factoring of the bottom one. Common factor I always look for, there's a common factor of 4. Pull it out, it leaves me with x minus 5. I factor it to that. Now what's said and done is I look, if I'm comfortable the factoring's done, and if it isn't, I'll figure that out in a few minutes. Okay? But otherwise I look for common factors, the x minus 5's cancel, and you can say I've got 2x over 4. Okay? Is that completely factored? Well, no, not really, because I can say that's 2x over 2 times 2, and these 2's cancel, and so I'm going to get x over 2. There's the simplified form. Now what this is telling me, again, if I go and ask for any x between negative a billion and a billion, if I plug it in here correctly, into this complicated thing, if I do it correctly, I'm going to get half of whatever x was. X divided by 2. The value is going to be x over 2. So if I plugged in 10, and I did it all correctly, I'm going to get 10 divided by 2, or 5. If it's a decimal, it's a decimal. Now the only thing I have to continue on is what are the non-permissible values. Now going from here, I know 4x minus 20 cannot equal 0. So 4x cannot equal 20. So divide by 4, x cannot equal 5. So going back to what I'm talking about, the only value of x you can't plug in is 5. Keep in mind, if I plug in 10, I get 5, but I can't plug in 5. Okay? If you ask for a negative a billion to a billion, 5 is the only one that doesn't work. Now you go on, and it's just more and more different examples about this. Okay? Looking at one like this. 2 times x minus 3 over 5x times 3 minus x. Okay? This is something, and it actually came up in some previous courses as well. You've got this sort of thing going on. You look at this and you're thinking, gee, that x minus 3, 3 minus x, they look almost the same. They're not, but they're close. So what I'm going to do is I'm going to show you what happens when you've got a binomial with a minus and then the reverse of that binomial, still a minus going through there. Here's something that happens. You have 2 over x minus 3, and I'm rewriting this. 5x times negative 1x plus 3. I just rewrote this. That's negative 1x, and that's a positive 3, so negative 1x plus 3. Okay? You don't have to do this as long as you remember a shortcut. What happens though is you have 2 times x minus 3. Okay, both of those pieces are factored as much as I can. Over here, in this second binomial in the denominator here, there's a negative 1 common. So if I pull that negative 1 out, I get 5x times negative 1, which yes, I could simplify that down. Negative 1 divided by the negative 1 I pulled out is positive 1. There was an x, I didn't pull it out, so it leaves me with x. Positive 3 divided by that negative 1 gives me minus 3. So I end up here. Now I've got x minus 3 top and bottom. Now the x minus 3's can cancel, and it leaves me with 2 in the top, negative 1 times 5x, or negative 5x in the denominator. Now, with fractions, that negative is there, or I could say that's negative 2 over positive 5x, or I could say that's negative in front of 2 over 5x. Either way, they're all the same thing. It doesn't matter. Okay? There's a single negative in a fraction. It doesn't matter whether you put it in the numerator, denominator, or just out in front. Single negative, that's what it does. So, same thing going on here. If I go and ask my friends for a number of x between negative a billion and a billion, and I plug it in here, I'm going to get negative 2 over 5 times whatever that x was. Okay? So if I have an x of 5, I'm going to end, I plug it in, x equals 5, I'm going to end up with negative 2 over 5 times 5, or negative 2/25. That's just what I'm going to end up with. Now, keeping in mind, in each case here, I need to think of the common denominator, or sorry, the non-permissible value. So 5x times 3 minus x can't equal 0. And we looked at these the other day. When you've got two things multiplied, either 5x can't equal 0, or 3 minus x can't equal 0. Okay? Here, divide by 5, I'll get x can't equal 0. That's a non-permissible value. So going back, I can't have 0. If I'm asking for my buddies, give me a number between negative a billion and a billion. 0 won't work. The other one that won't work is coming out of here. If I move that x over, I'm going to get 3 cannot equal positive 1x. So x can't be 3 as well. My two non-permissible values are 0 and 3. So when I'm asking for a number between negative a billion and a billion, if you give me 0 or you give me 3, the whole thing falls apart and I'm not sure what's going on. But if I take any other value, plug that in, I'm going to get negative 2 over 5 times that value. Okay? The basic rule here is that if you have x minus a over a minus x, okay, that's the basic rule. If you remember this, those things there, they look very similar. You have x minus a over a minus x. That simplifies down to negative 1 over 1. Okay, or negative 1, depending on how you want to look at it. But there's basically they cancel, but they leave a negative. Now, keeping in mind with the negatives, it can be in the bottom, the top, or right out in front. It doesn't matter. But this is the basic rule. I'm going to put this in a little cloud just to draw attention to it. Okay, but that's the basic rule there. Now, any other rational expressions, it's the same idea. Factor top, factor bottom, cancel out. Okay, so I end up with one like this. This is my last example for this, and then I'm going to do a few more things. If I end up with x squared minus 1 over 1 plus x. Okay, now this rule is only minuses, so it's not going to occur here. But I have this. Well, I look in the top, and what I realize is I have x squared minus 1 squared. Okay, so that's going to become first piece x plus the second times the first piece x minus the second over 1 plus x. Now with the negatives, the idea is they cancel out, but they leave a negative behind. When it's addition, doesn't matter. X plus 1, 1 plus x, same diff. They're fine. So they just cancel if it's a positive. What that leaves you with is x minus 1 over, and in the denominator, there's nothing there except for that invisible 1. If you write the invisible 1, that's fine. If you don't write the invisible 1, that's fine. Essentially, x minus 1 is what it simplifies down to. Keeping in mind what we said, if you pick a number between negative a billion and a billion and plug it in for x, okay, you're going to get one smaller than whatever the x was. So if I plug in the answer of 22, or plug in a value of x of 22, I'm going to get 22 minus 1, or 21, after all is said and done. Now, keeping in mind I still need to look at non-permissible values, so 1 plus x cannot equal 0, so subtract the 1, x cannot be negative 1. Now, that's the only non-permissible value. If I'm asking for a number between negative a billion and a billion, negative 1 is the only one that doesn't work. Okay, so that's the situation there. Those are just some examples of various things. Essentially, what you've got in each case is you've got the factoring idea. Now, a couple other little things that are going to come up. Okay, one is same basic idea, just using exponents. Okay, we like these questions because they really test to see whether you know the math. E.g., I want you to simplify 45 x squared y z cubed. Now the y is to the exponent 1. Notice there's no exponent on the y. There is that invisible 1. Okay, so 45 x squared y z cubed over 60 x y squared z. Now, this is using exponents as well, which is part of the course a little bit later on, exponents and logs, but it's kind of a cross between both. So I look at this particular situation and I'm going to look at the numbers. What can I divide each of those numbers by? So I'm going to factor it a little bit. That's going to be 5 times 9 over, I can pull out a 5 there, so I'm going to get 5, I'm going to get 12. And then with the letters, I'm just going to go along and do some cancelling. If there were 2 x's in the top and I'm dividing by 1 x, it's essentially there were 2 and I'm pulling 1 out. So there were 2 in the top, I pulled 1 out, there's going to be 1 left. And it's always in the numerator, so x to the power of 1. Here, if there was positive 1y in the top and I pulled out 2, okay? There was 1 and I pulled out 2. You say, well, that doesn't make any sense. But we're working with numbers here, so let's work with that. If there was 1 and I removed 2, how many do I have? I have negative 1 of them left. Here with the z's, there was 3. I pulled out 1. Okay, so there are 2 z's. Okay, so I've got that. That's nice and easy. Okay, so then I'm going to go through the 5's cancel. Okay, and I'm essentially going to end up with 9. I've got x to the power of 1, y to the power of negative 1, z squared over 12, because that's all that's left there. So then I think, can I still clean this up? Well, 9 and 12. If I pull out a 3 out of each one of those, it's going to be 3 times 3, x, y to the negative 1, z squared over, here 12 is 3 times 4. And those 3's cancel. So I'm going to end up with 3 x y to the negative 1 z squared over 4. Okay. Now if you remember exponent laws from 10 common, that exponent of negative 1 just isn't allowed. So you can take that part, just that part alone, and flip it down. And you end up with 3 x z squared in the top, and in the bottom I'm going to have 4 y to the power of positive 1. Okay, that's an exponent law you have before. Okay, so that's that. Okay, looking back at the original question, what are my non-permissible values? Well, I know that 60 x y squared z can't be 0. 60 can never be 0, so I'm going to ignore that. This tells me that x cannot equal 0. It tells me here that y squared cannot equal 0. To finish that, you take the square root. Y cannot equal. Square root of 0 is 0 still, so that's that. The other non-permissible value is z cannot equal 0. So if I picked a number for x, y, and z, plugged it in, I'd get basically this formula. It's a little bit simpler to use. The only ones I can't use are zeros, x, y, and z. Now, keeping in mind what we were talking about the other day, just because non-permissible values are involving 0 doesn't always mean that 0 is a non-permissible value. It is in this case, it's not in the others. Some people will say, Shaughnessy, 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 can't we do this a slightly easier way? Sure you can. There's lots of different ways to do most of this mathematics. So taking the same question, here's looking at this. 45x squared y z cubed over 60x y squared z. Here's another way of doing it. Still taking the 5's out of the 45 and the 60, I'm going to get 5 times 9. Now x squared gives me 2 x's, so I'm just going to put 2 x's there. Y gives me 1y. Z cubed gives me 3 z's. So I do that. Some people really like this method, so please feel free, if you like this, do it. The 5 out of the 60, that leaves me with the same 12 I had before. Here I've got 1 x, here I've got 2 y's, and here I've got a z. Okay? So if you think about it this way, the 5's cancel. What else cancels? There's an x that cancels. 1 is left in the top. Here there's a y that cancels. Doesn't matter which one. 1 is left in the bottom. Here there's a z that cancels. The 2 are left in the top. And so my next step is the same as I had before, just with the y right in the right spot. 9 is in the top. There's a single x in the top. There's 2 z's in the top. In the bottom I've got 12 and I've got 1 y. So then I don't need to think about the negative exponents. If I look at it this way, the negative exponents aren't part of it. Now I just need to finish it off with the 3. So I'm pulling out the 3 out of the 9. So I'm going to get 3 times 3 squared of xz squared over 3 times 4 times y. The 3's cancel. I'm going to end up with 3xz squared over 4y. Same as I had before. That's the situation there. Now, what sorts of things have we seen on diplomas? We've often seen if that expression is simplified down to the form ax z to the power of b over 4y to the power of c, what are the values of a, b, and c? They're just using spots, A, B, and C. So essentially you have to do that. And you have to recognize from here, well, A would have to be 3. B would be the power of Z. B would have to be 2. And C would be the power of Y. C would have to be 1. And so that's what you'd put in. You'd put in that sort of thing. So those are sorts of questions that you might see. Other things that go along with this, they will ask you the following, and you need to recognize that sometimes we'll start with the simplified form and we want you to go backwards. So here, an expression has NPVs, non-permissible values, of 5 and negative 3, and it simplifies to 4 over x minus 5. What was the original expression? Okay, so it simplifies, oops, there we go. An expression has non-permissible values of 5 and negative 3. Simplifies to this. What was the original? Well, how I usually look at these depends on how much you quickly see this. This particular guy here simplifies. It says that x minus 5 can't equal 0. So it says x can't equal 5. That's what the simplified form says. Okay, so I've got the 5. I'm good with that. That's there. But I need the negative 3 in there as well. So I know that x cannot equal negative 3. So if x cannot equal negative 3, move it over. And I know you're not used to doing this, but it tells me that x plus 3 can't be 0, because I just took this 3 and moved it over. So what this is telling me is that I'm missing an x plus 3. Somewhere along the line I'm missing an x plus 3. So I have 4 over x minus 5. Okay, and I have that, and I just put brackets in there for now. I need another x plus 3 down here. Okay, But the key thing all the way along is you can only multiply by 1. So it leads to that rule, whatever you do to the bottom, you have to do to the top. So I have to put a 4 times x, or I have to put an x plus 3 in the numerator. So when I clean this up, the original expression had to be something like this. 4 times x plus 3 over x minus 5 times x plus 3. And that's what I'd start to look for. Okay. Now they could have done a variety of different things. They could put the 4 in, so they'll get 4x plus 12 over this denominator here, that sort of thing. But that's an example of working backwards. It says these are the NPVs, and it's simplified to this. Okay, so you've got that. The only other sorts of things that might happen is questions like this, e.g. Marcus made an error. Okay, in his simplification, and in the simplification of the expression 4x squared minus 16 over 8x plus 16. Okay, so you've got that. And they'll also tell you the non-permissible value. I'm going to tell you that x cannot equal negative 2. Okay, they'll tell you that just because it's there. Now what you've got is you've got steps. Step 1. Okay, step 1 looks like this. Step 2 looks like this. Step 3 looks like this. Sorry. And step 4 looks like this. Now, there's a mistake here somewhere. That's the question's already gone and said that. Where's the mistake? Okay, Marcus made an error in this simplification. Where's his mistake? And you just have to go through and follow along. Now, don't always jump to conclusions that it's always step 1 or always step 2 or 3. It's not always. It just is not always. So I go through and say, well, what has he done here? He has factored out the 4. So if I factor out the 4, that'll leave me with x squared minus 4. That looks good. In the denominator, he's factored out an 8, 8x plus 2. My first thought, that looks pretty good. Here he's gone through and he hasn't shown all his work, but what he's done is he's cancelled with the 4 and the 8 because he recognized the 8 was the 4 and the 2. So he goes and cancels the 4. So that should be all well and good. But if he did, that should be 2. Right there. Okay. Now what sort of mistakes are they going to make? They're going to make any sort of mistakes. Do not jump to conclusions. They're going to make the sorts of mistakes that often students make. So please watch for that. So the first error, the first completed error, step 2. This is the first error. Now there may be more, okay? I don't know. But often you'll ask you to find the first error. And I could ask you to find it and correct it, so fix it. So you've got to go through and do that. This is the process that I use when we're working on homework. And you say, look, I'm doing this, but I don't get the right answer. So you have to follow along, step to step to step. It's one of the reasons why writing out your work is really important. Because if you don't write out your work, it's really hard to figure out where you went wrong. I hope that makes sense. I hope that works for you. I'm just going to check to see if there's anything else I had in my notes. No, that's it. If you need more examples, there's more examples in class. Otherwise, good luck on the homework and we'll see you soon.